In this video, we're going to study a way to write numbers called the scientific notation. The way you usually write numbers like this is called the standard notation, but sometimes these numbers are very, very large. You have a lot of numbers attached to them, a lot of zeros, a lot of other numbers, and it's just more efficient to write it in this notation here called the scientific notation. They're both equivalent in terms of numbers, it's just that they're written in different formats. The scientific notation has two parts to it. There's a coefficient part, which is the kind of that regular number part that you're used to seeing. And then there's the base with the exponent. So it's usually some number times 10 to the power of something. And we're going to see how to convert a number into this scientific notation. We're going to see how to convert a standard number into the scientific notation that you see over here. So our learning goals today are to convert regular numbers, but they're more appropriately called standard notation, to the scientific notation. We're going to see how to convert scientific notation into standard notation, so basically working backwards. We'll see a few operations regarding scientific notation, so multiplication and division is what we'll focus on. We might briefly see addition and subtraction, but really for grade 9, you're going to see mostly multiplication and division. That's the most important part. And you just need to understand what scientific notation is really used for. So the scientific notation is a very useful tool in science. It's used when you're trying to write some very big numbers, like you can see here. The temperature at the center of the sun is 15 million Kelvin, which is a unit of temperature, or very small numbers that are long to write, like 0.000000, so on and so forth, 1673 kilograms. You don't want to have to write that out every single time. So what we do is you write it in this format here. So the 15 million we saw earlier, the 15 with 6 zeros, is 1.5 times 10 to the power of 7. And that's the scientific notation. The parts of the scientific notation include something called a coefficient. So you can see here that 1.5 is a coefficient. There's a multiplication sign all the time. And following that, there's a 10. So there's always that 10 to the power of something. So for example, here we have to the power of n. That just means some number. And we can figure that out with a few rules I'll teach you in a bit. So here you can see to the power of 7. Now, the other thing I need you to remember is that for the coefficient here, this number here, it needs to be a non-zero digit as your first digit. So if you have 0.5 as your first digit, that's incorrect. It's not proper notation. This first digit here has to be a non-zero digit. So for example, 1.5 would work because that first digit there is a non-zero digit, or 2.5 or 3.5. The other thing is that there can only be one number before the decimal place. So 1.5 is appropriate, but something like 25.5, that's not appropriate because there's two numbers to the left of the decimal place. More appropriately, this would have to be 2.55. That's more appropriate because now there's only one number before the decimal place. And I'll teach you how to manipulate your decimal place and how it affects the scientific notation throughout this video so you can get the proper form. So again, we have our coefficient, our multiplication sign, our base of 10, we call this a base of 10, and an exponent that we figure out based on how we move our decimal place. Now, I said that the scientific notation was used to write big numbers and small numbers, but it's also used to make significant digits less ambiguous. So if you've seen a significant digit video, you'll understand what I'm talking about. If you haven't, make sure you watch it and make sure you pay attention to the lesson your teacher will give you on significant digits. So let's say, for example, you had the number 100. In this case, the rules you would learn for significant digits state that the trailing zeros would be non-significant. So you'd only have one significant figure or digit. Significant figure, significant digit, same thing. Now, let's say, though, that you wanted this to be significant, or you want to make it clear that, that the zeros are non-significant. You want to make it really clear. If you write it in scientific notation like this, 1 times 10 to the power of 2, you're showing that you only have one significant figure, that 1 there. Okay, you're being very clear. But let's say that you wanted to express these zeros as being significant. You can actually write 1.00 times 10 to the power of 2. And what that illustrates is that these two zeros are significant because anything in the scientific notation is considered significant digit, except for the base of 10 and the exponent, but anything in the coefficient area is considered significant, so you would have expressed here that these zeros are actually considered significant. And if you didn't want that, you simply put 1 to show that those zeros in the 100 there are not significant. And again, we'll see how I converted that to get the 10 to the power of 2 in a bit, but just understand that it makes significant figures in some cases less ambiguous or less confusing, more clear to the person who's reading those numbers out. So we're going to see a few examples of how to convert numbers, standard notations, into scientific notation. Here we have the number 1,234 and 56 hundredths. So what we're going to do is we're going to see how to convert this into scientific notation. The trick is finding your decimal place first. So here's your decimal point over here. And what you want to do is you want to move this decimal place to be in between the first digit and the one that follows it. So basically to be right after the first digit to the right of it. And so what you do is you count how many spaces that would be. So you take that decimal and you start counting. You go 1, 2, 3. So when I move that decimal place, I now get the coefficient 1.234, 5, 6. Then I do times 10. And the exponent, I figure it out based on how many times I moved the decimal. I moved the decimal 3 spaces. Now when you move towards the left side, your exponent is going to be positive. You're not going to put a negative sign in the front of it. It's going to be positive. Now if you actually put this into your calculator, 1.23456 times 10 to the power of 3, and you press equals, if your calculator is programmed properly, you'll get this number again. They're equal. They're the same thing, except this is written in the scientific notation. So you count the number of spaces you move to get your decimal to the proper position. If you move to the left, you make sure that your exponent is a positive power. Don't forget to put that times 10 here. Okay, so here we have the scientific notation. Sometimes you might need to move your decimal towards the right. So we'll do this example over here, where we have 0.00657, and we need to move that decimal to the right to get it right here, right after that 6, because that's the first digit that will appear in our scientific notation. So we went 1, 2, 3. We moved 3 spaces. When we do that, we get the coefficient 6.57, because our decimal is in between the 6 and the 5 now, times 10 to the power of 3. Now because we move to the right, when you move to the right, you make that a negative exponent. And so if you put this into the calculator, you'll see you'll get this number over here. The negative exponent really shows that you have something less than 1, like 0 point something, 0.1, 0.2, 0.3, 0.005. That's what that negative part really is expressing here. If you put this as a positive number, you'd have a very large number. So negative exponents are to be seen as basically you have a small number, and positive exponents means you have a larger number, something higher than 1 or higher than 0.9999999. So now we're going to do an example together. Here you have all the steps written out for you. We saw an example on the previous slide, but here you can see all the steps that you're required to do. So we have over here 51,000.0, and we need to change this to the scientific notation. So here's our standard notation. We're going to change it to scientific notation. You grab that decimal place and count how many spaces you have to move it to get the decimal between the first digit and the second. So 1, 2, 3, 4, and it becomes 5.10000. And I'm just keeping the same number of significant figures that there was in my original standard notation. So now that I have this decimal here, this number over here, what I'm going to do is I'm going to multiply it by 10. I need to figure out what I have to put the 10 to the power of, because based on how many steps I moved or how many spaces I jumped with my decimal. So since I moved over to the left 4 spaces, what that means is that the exponent is going to be 4. So I have 5.10000 times 10 to the power of 4. This is scientific notation, so all these figures here are significant. So what that means is that I have 1, 2, 3, 4, 5, 6 significant figures. Don't count 10 to the power of 4 as a significant figure. So now we'll do a few examples together. What you should do is maybe pause the video, try them yourself, and then compare to see if you're on the right track. So we'll start off by doing the first question here. We want to convert the standard notations into scientific notation. I know you don't see a decimal place here, but when you have a number like this, a large number, or a number that's not 0.00 something, well, the decimal is typically going to be at the end if you don't see one, so here. So you can just place your decimal there. We have 3 significant figures in this, and if you haven't done a significant figures video yet, ignore the significant figures parts and then come back to this afterwards for the significant figures talk. So we know that our scientific notation needs to be 6.07 times 10 to the power of something. So I count how many spaces I have to move this decimal point to get to between 6 and 0 there. So I move it 1, 2, 3, 4, 5, 6, 7, 8. 6.07 times 10 to the power of 8. You can try this one over here. Decimal will be at the end here. So I'm going to have 1 times 10 to the power of something. I move the decimal 1, 2 to the left. So 1 times 10 to the power of 2. Notice in this case I only have one significant figure because the trailing zeros are not significant. Now if you intended for those zeros to be significant, you'd simply put 1.00 times 10 to the power of 2, just to show that precision a little bit more. So if you put this in your calculator, just a reminder, when you do the 1 times 10 to the power of 2, you're just going to get 100. They're the same thing. It's just that one is written in scientific notation and one is written in standard notation. Now let's take a look at some larger numbers here. We have 64 million, and we want that to be in the scientific notation. So we know we're going to have 6.4 times 10 to the power of something. Now again, these digits here are not significant, but these two are, so we're just going to keep the 6.4 there. So let's count how many spaces we had to move to get 6.4. 1, 2, 3, 4, 5, 6, 7. 7 spaces to the left, so 6.4 times 10 to the power of 7. Let's go to number 4 now. So again, you should always pause the video before I attempt it, and then you try yourself. So we know we're going to make this 9.56 times 10 to the power of something. Let's count how many spaces we had to move our decimal. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 9.56 to the power of 23. It's positive 23 because we moved towards the left. Now we have another example here, similar. We're going to have 9.56 again, but this time you'll notice that your decimal will not be moving towards the left, it will be moving towards the right side. So what that means is your exponent needs to be a negative exponent. The number for that exponent specifically will be determined by how many spaces we moved our decimal. So here's our decimal. Let's start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 9.56 times 10 to the power of negative 25. If you put this into the calculator, assuming your calculator could fit that many digits into it, you would see this number here given to you. Now we have one that's a bit interesting. We have 4.7, and you'd have to convert that to scientific notation. Now you'll notice if you have 4.7, you don't have to move your decimal anywhere. It's already in the correct position. So we have to do times 10 to the power of something, and since we didn't move our decimal, you can simply put times 10 to the power of 0. And this is actually still equal to 4.7 because anything, a number to the power of 0 is going to be equal to 1. So 10 to the power of 0 is equal to 1. So what you're actually seeing here is 4.7 times 1, which is 4.7. But this is the proper scientific notation method. So now we're going to do the opposite, where you're going from scientific notation to standard notation. We'll start off by doing this example over here, number 1. So we have 1.5 times 10 to the power of 3, and let's analyze that. So we're kind of going backwards. When you have a positive exponent, that means that you had to move your decimal to the left to get that positive exponent. So you're rewinding, you're going towards the right now. You're multiplying by a positive exponent, so you're going to be moving towards the right side, and specifically 3 spaces. So we're going to have the 1.5 here. Start counting, so make a nice thick dot here to show your decimal, just so you don't get confused with where it is, and start counting 3 spaces. So 1, 2, 3. That last space there that you arrived on, that's where your decimal place will be. And any place where you see a peak where your decimal was not, so is not currently or was not before, you're going to put a 0 there. So you have 1, 5, 0, 0, and we're not going to put a dot at the end. We just have that dot there to show us where the decimal is, but we're going to have 1, 5, 0, 0. 1,500. If you left the dot there, so if I wrote 1,500 with a dot at the end, that would mean that all my digits there are significant. I want to try to keep the same amount of significant figures. So there's 2 significant figures here. I'd have 2 significant figures in this answer over here. Okay. Next, we're going to try number 2, where it's sort of the opposite situation. You have 1.5 times 10 to the power of negative 3. And so in this case, we know to get the negative exponent, we had to move our decimal to the right. So to rewind, we have to go to the left 3 spaces, specifically because it's to the power of negative 3 there. So make a nice thick dot here to show that this is where your decimal begins, and start counting. 1, 2, 3. It ends up right here. Now in this case, you do have to put a 0. When you're moving towards the left, you're going to have 0.0 something. You can't just put point something. You have to put the 0 in the front to have the proper format. So you have 0 point, and then you're going to put a 0 where the peaks are over here. So 0 and 0, and now you can rewrite your answer as 0.0015. Now there was a decimal between the 1 and the 5, but you moved that decimal, so it's no longer there. Let's try another example out. Let's try number 9. So you should pause the video and try this out yourself, and then check if you are on the right track. So we have 1 times 10 to the power of negative 1, and you might be confused as to where your decimal is, but when you have a whole number like this, the decimal is on the right side of it. So just make a little decimal here, and you're moving to the left once. So 1 over here, put your decimal here, and put a 0 before it. So we have 0.1. Now, another one you can try is number 10. You can try all of these. The answers are actually posted online in the worksheets that I posted, so you can go verify them. But if you try number 10, this one's actually very straightforward. You'll notice you don't have to move your decimal at all. Let's just say it was here. You don't have to move it at all because you have times 10 to the power of 0, which is really 1, as we saw in the previous slide. So we now put 4. It's really like saying 4 times 1, which is equal to 4. So you should attempt the rest of these problems here. One of the ones that students often have trouble with is this one here, number 8, and we'll write it out and try it together. So 1 times 10 to the power of 4. And I'm actually going to add another example here to show you by comparison. Let's do 1.2 times 10 to the power of 4. So if I was doing 1.2 times 10 to the power of 4, that one's a pretty easy one. Students usually grasp the fact that there's a decimal there, and they'll start moving the decimal. They'll go 1, 2, 3, 4, and here's their new spot. And they'll put a 0 here, a 0 here, a 0 there, and they'll get that that number is actually 12,000. Now, when you don't have that decimal point there, it can be a bit confusing. So for the purpose of this, what I would do is, if you don't have a decimal point, I would add a decimal point and make it 1.0, just for the counting. It makes it easier. And then start counting your spaces. So 1, 2, 3, 4. Here's your new decimal place. And you have 0, 0, 0. And so that gives you 10,000. So if your decimal place is not there, it's okay to add that when you have a whole number like this, just so you don't get confused and lost when you're doing your counting and you're jumping around. Okay? When you had a number like this one here, a whole number, you didn't really need to add the decimal like we did here. You didn't have to add the decimal to the right of it, only because we were moving to the left, so there wasn't too much confusion there. So try these ones out here. Go verify your answers. And if there's any issues, make sure you watch the video again for how to convert from standard notation to scientific notation, and research some other videos. There's some video links that are at the end of this PowerPoint that you can also review. Ask your teacher. There's many resources available to you. In the next part of this video, we're going to go and take a look at some operations with scientific notation. So we're going to take a look at multiplication, division in some detail, and then there's some slides where you can review addition and subtraction yourself. But we won't be doing too much of the addition and subtraction in grade 9. So again, now we're at operations with scientific notation with a primary focus on this multiplication and division portion of the operations. So the general rule is when you're doing a scientific notation multiplication, you have to follow the significant figure rules. So the least number of significant figures is what you'll be reporting in your final answer. And usually what you want to do is you want to start off by multiplying the coefficients, so the numbers that are not 10 to the power of something. So we have 2.00, 2.00, and 4.00. They each have 3 significant figures. And again, if you haven't seen the sig fig videos yet, ignore the sig fig part and come back to this later. So we have 2.00 times 4.00, which is 8.00. So we did that multiplication, as you can see here. So first you multiply the coefficients, and then you multiply the tens to the power of numbers, your base and your exponents. When you do that, because they're both a base of 10, that base number is 10, what you can do is, because you're multiplying, you add their exponents up. So 10 to the power of, I'm just going to write this out here, 10 to the power of 3 multiplied by 10 to the power of 4 is actually 10 to the power of 3 plus 4. You're just adding the exponents up. And so you get 10 to the power of 7. So your final answer is now 8.00 times 10 to the power of 7. We'll try a few examples together here. So let's take a look at 4.3 times 10 to the power of 8 multiplied by 2.0 times 10 to the power of 6. So usually, just to keep things nice and clean, and we know the order of operation, we put each scientific notation in its proper bracket, and you would do that in your calculators too if you were doing it with your calculator. And now we can go ahead and try this out. So first we're going to do the 4.3. We're doing this into 2 steps here. 4.3 multiplied by our 2.0. They have 2 significant figures each, so we'll report our answer to 2 significant figures. And that'll be 8.6. So we have the first part of our number written out. Now we just need to do the 10 to the power of 8 times 10 to the power of 6. So 10 to the power of 8 times 10 to the power of 6. And that's going to be 10 to the power of 8 plus 6. We're adding the 8 and the 6 up when you multiply something with the same base, which is a base of 10 in this case. So 10 to the power of 14 here. Now that we have our 2 parts, we just simply have to connect them together by a multiplication sign. So we have 8.6 times 10 to the power of 14. Forgot my 1 there. There you go. You can pause the video and try B and then check if you are on the right track. So again, our first step is to do the multiplication. So 6.0 multiplied by 1.5 and that's going to be 9. And we'll do 9.0 because it's two significant figures. And then we have to do our 10 to the power of 3 multiplied by 10 to the power of negative 2. And so you have to be careful here. We know this is going to be 10 to the power of 3 plus negative 2, which is like saying 3 minus 2. When you have a plus and a minus there, 3 minus 2. Because you're docking, you're taking away numbers from that 3 there. So it's going to be 10 to the power of 1 because you're adding a negative 2 there. So our final answer is going to be 9.0 times 10 to the power of 1. Now normally if you have an exponent of 1 you don't have to write it down because it's implied. That just means that we know it's there. It's implied, it means we know it's there. But for the purpose of the calculations that we're doing, I do want you to write down the exponents of 1 just so I know that you know what that means. And now we're going to go and we're going to try this one here. This one's a bit different than the ones we saw above. It's the same steps, but there's something different about it. So we're going to start off with our multiplication here. 1.5 multiplied by 8.0. They both have two sig figs, so we're going to keep 2 digits when we do our multiplication, but that should be 8, so that should be 12. Okay, and then you're going to do your 10 to the power of negative 2 multiplied by 10 to the power of negative 1. And we're going to get 10 to the power of negative 2 plus negative 1, which is basically negative 2 minus 1. And that gives us 10 to the power of negative 3. And so far everything looks fine. Everything looks okay, we're on the right track. We're going to write our final answer here, 12 times 10 to the power of negative 3. But we do have a problem. You may have noticed that we have our coefficient here is 12. Remember, the coefficient has to be a number where you only have one number before the decimal. So for example, 1.2, that would be an appropriate scientific notation coefficient to have, but we don't have that here. So we have to move our decimal place. So our decimal place will be at the end here, and we need to move it over 1 to get 1.2. Now remember that when you move your decimal over to the left, what you're doing is you're adding 1 to your exponent of 10 here. So we're doing plus 1. So this 1.2 times 10 to the power of 3 becomes 1.2 times 10 to the power of negative 2. If you had to fix this by moving your exponent by moving your decimal to the right, you would take away 1. So you just need to make sure that in the end your format is appropriate. Otherwise, this would not really be considered the appropriate scientific notation, and you wouldn't get full marks for it. So just pay close attention to that when you get problems like this. You will see some in the booklet that you're given. So now we get to divisions, and we'll see that divisions are actually very similar to the multiplication, except you're dividing, and when you divide, rather than add exponents, you subtract exponents. So in this case, we have 9.60 times 10 to the power of 7 over 1.60 times 10 to the power of 4. And so we first do our division, 9.60 divided by 1.60, that gives us 6.00. We kept it to 3 significant figures, multiplied by 10 to the power of something. So we have 7 on top, 4 on the bottom. Since there's a division, we subtract. You do 7 minus 4. You do the top one minus the bottom one, and you get 10 to the power of 3 over here. This line, in case you're not familiar with it, simply means division. It could have been written with the division sign that you're used to, like this as well. But when you do something over something and you have a line there, it means division. So let's do this example together here. D, There's a few more examples in the packet that you're given. So you have 7.8 divided by 1.2, and that's going to be equal to, so if you put that in your calculator, 7.8 divided by 1.2, you get 6.5. And then you have to do your 10 to the power of 3 over 10 to the power of 4. And now you're going to have 10 to the power of the top one minus the bottom one, so 3 minus 4. And so that's going to be, 3 minus 4 is not going to be 1, it's going to be negative 1, 10 to the power of negative 1. So our final answer here is going to be 6.5 times 10 to the power of negative 1. Let's try another one out. Let's try E. So I'm going to start off over here. I'm going to do 8.1 divided by 9.0. 8.1 divided by 9.0, and that gives me 0.9. Because there's two significant figures, so I keep this to two significant figures as well. Okay, great. We have our first part done. Let's do our second part now. So 10 to the power of negative 2 over 10 to the power of 2, which is going to be equal to 10 to the power of negative 2 minus 2. Oops, minus 2. So minus 2 minus 2 is 10 to the power of negative 4. And now we can put our answers together. We have 0.9 times 10 to the power of negative 4. Now there is a problem here you may have noticed already. Over here, we need to make sure that when you have scientific notation, you have a non-zero digit as your first digit. If you have a 0 digit as your first digit, it's a little bit off. You need to make sure you convert that to a non-zero digit. So what we need to do is move our decimal place over by 1 to get 9.0 times 10 to the power of something. Now when you move your decimal place over to the right side, you're taking away 1. You're doing minus 4 minus 1, which will make this minus 5. So same steps, it's just you have to make sure that you have the proper format in the end. That digit there has to be a non-zero digit as your first digit. So here you have an example where you need to do multiplications and divisions. So what I recommend is that you simplify the denominator first. So basically do that multiplication there first, and then rewrite it in a neater way where you only have two scientific notation numbers, and then do the division at the end. So I'm going to start off by doing that. You can pause this and try it yourself, see if you get the right answer. But I'll start off by doing that little multiplication piece, of 2.4 times 10 to the power of 4 multiplied by 1.8 times 10 to the power of negative 2. So I'm going to do the 2.4 part multiplied by 1.8 and there's two sig figs for each number, so we'll have two sig figs there, times 1.8, and we get 4.32. Since it's two sig figs, I'm going to round it to 4.3. I'm rounding down because the 2 there is not higher than 5. So I have 4.3, and now I'm going to do the 10 to the power of 4 multiplied by 10 to the power of negative 2. I know overall there's a division happening here, but at the bottom here it's just the multiplication. So I'm just carrying that out first. So I'm going to have 10 to the power of 4 plus minus 2, which is like saying minus 2. And we get 10 to the power of 2. And so our final answer here is going to be 4.3 times 10 to the power of 2. So now what I can do is I can rewrite this whole equation here as 6.48 times 10 to the power of 5 multiplied by 4.3 times 10 to the power of 2. And now I can carry out this whole division. So I'll start off by doing my 6.48 divided by 4.3, and there's two sig figures that the 4.3, so I should have two sig figures in the end. Remember the least number of significant figures. So let's do 6.48 divided by 4.3, and I get 1.5. Two significant figures there. And now I'm going to do my 10 to the power of 5 over 10 to the power of 2. So it's going to be 10 to the power of 5 minus 2, which is 10 to the power of 3. So our final answer is going to be 1.5 times 10 to the power of 3. So what we've seen so far are the how to convert from standard notation to scientific notation and vice versa. So from standard to scientific, from scientific to standard. We've also seen how to do some multiplication and divisions using the scientific notation. And do make sure that you're following your significant figures rule. It's important that you do watch the significant figures video or pay attention to the significant figures lesson that your teacher has done or will do for you, so you can apply those rules. The next few slides do have some examples of how to add and subtract significant figures. I'm not really going to go through that because we're not going to see it too much in grade 9. I might do one quick example and the rest you can do on your own. You'll see that most of the sample problems that you'll get will be multiplication, division, and converting from standard to scientific and scientific to standard. At the end of this video, you'll see a slide that has some suggested homework questions. Those will be posted online. There's some answer keys with them, along with the skills notebook or introduction booklet that you have to complete as assigned by your teacher. So just very quickly, I'll walk you through how to do an addition. The same rules will apply to subtractions. So when you have an addition, again, notice you'll see the plus sign. Subtraction, you would see the negative sign. Instead of a X or a line or a division sign. In this case, you want to be able to add. You want to be able to add the coefficients up together, but you can't do that unless your base of 10 on both scientific notation numbers have the same coefficient. And you can actually modify that coefficient simply by moving the decimal. So you can make this 2 over here a 3 by moving the decimal of your 3.4 over 1 to the left, because when you move to the left you add 1. And so you get 0.34 times 10 to the power of 2 plus 1, which is 0.34 times 10 to the power of 3. Now I know this here isn't the proper scientific notation format, but it's okay. We can use this right now to do our calculation to get to the proper scientific format. So now that we have the bases of 10 to the same exponent to the power of 3 here, what you can do is you can simply add up your coefficients. 0.34 plus 4.57, that gives you 4.91, and then times 10 to the power of 3. So you leave your times 10 to the power of 3 as is. You're not really changing those up at all. And so you can do that for these problems over here. Move the decimal to get them to the proper, to get your 10s to the same base, to the same exponent, and you do the same thing for a subtraction. If for some reason you get, when you add your numbers up, you get, let's say, something like this, 15 times 10 to the power of something, remember that you need to move that decimal place over. Or if you get something like this, 0.9 again times 10 to the power of something, remember that you need to move that decimal over as well to get the proper scientific notation format. Otherwise, you will have marks deducted because you wouldn't have follow the scientific notation rules. And here are some more practice problems that you can attempt, except these ones here are subtractions instead of additions. So for homework, you should complete the worksheets that were provided to you by your teacher for scientific notation. There's a few more videos over here that you can watch in the event that this video is not clear enough or you need some more support or other examples. The video at the bottom here is a scientific notation along with significant figures video, where you can see multiplication, division, and significant figures being taken into account. So again, scientific notation was a system, or is a system that's used when you're writing really, really big numbers, like this one over here, or really, really small numbers, like this one over here. It helps to make significant figures less ambiguous, meaning less confusing. So if I have 100 here, generally the trailing zeros without a decimal place are non-significant. They're not significant digits, so you only have one significant digit. But let's say you did want these zeros here to be significant. There's a few ways you can do that. You can do 100 point like this, but typically you could also simply convert these into scientific notation, 1, 2, and you get 1.00 times 10 to the power of 2. And now we know for sure that those zeros are meant to be significant. If you didn't want them to be significant, you would have simply written 1 times 10 to the power of 2 and left those zeros out, because everything in scientific notation is significant, but don't count the exponent and the base here. But anything in the coefficient portion is significant. So it does a variety of different things for us, and it's a very useful application. You should know how to work scientific notation because you will see it in more detail when we get to the space unit, and also when you get to grade 10, you'll see it in the optics, and then when you get to grade 11, if you take chemistry and other courses like physics, you're going to see a lot more scientific notation as well.